Hey there, welcome back to the next video in this series of angle bracket free body diagram analyses. I have covered various types of free body diagrams on these angle brackets in the previous videos on my YouTube channel. You can go take a look at those. The previous brackets were analyzed for vertical loading, horizontal loading, and in-plane loading, different kinds of loading. In this video, what I would like to cover is a combination loading or combined loading. And then what we will do is at the end, we're going to superimpose all the reactions that we will calculate to find out what the final Fastener reactions would be. So I can't wait to share this information with you. So let's get started. All right, so let's get right into it. Let's go to the next slide here. We're going to look at the angle bracket loads, combined loads this time. Now you have seen a picture like this before. A few times you have seen a load going up like this, and that's the only load on this bracket. A load going to the right, either this way, or a load going to the right, left to this way. But this is the first time I'm going to combine a load also going in plane along this edge with a vertical load. Now I could add another load here, but it's just too complicated for the purposes of this video. I mean, we can do it, but I wanted to keep it relatively simple for the hand calculations part. So this is going to be our basic model with applied loading, and as we know, these two fasteners are pinned, constrained, and we're going to start with the free body diagram of this bracket with only the PZ load, right? So we're going to split out the free body diagrams for each of these loading types. So the first one would be this, and you know this already if you watched the first video on the angle bracket heel toe prying loading video. And this is where we resolve the heel toe reaction load and the fastener reaction load, tension load, using this vertical PZ. So if you want to know more about this particular type of free body diagram, go back to that first video on my YouTube channel, and I'm just going to show this to you here, but we're not gonna go too in depth into this itself. So the next one would be the free body diagram due to this PY. So let's separate that out, and that's going to be this guy here. A very complicated looking free body diagram. Believe me, it's really not that complicated once you break it down. Essentially what you see here is we have this Y load going over here. So this thing produces various different kinds of reactions at these fasteners due to the moments and the loading that is going in plane. First thing obviously you'll notice is you have the RY at the two fasteners, which is equal, and then that's a direct reaction of PY. And then you also have the RX1 and the RX2 in the X direction, and you might be wondering how in the heck would that happen. Well, if you have read my blog post on shear clips, then you will know what this is all about. All right, so this guy here is going to produce a moment that's turning this angle bracket base, which produces these reactions. Okay, so that's horizontal here, and then you also have the vertical, obviously, because of both this guy here, but then you also have an overturning moment about the x-axis that also produces these two different reactions. So this is your free body diagram for PY. All right, so let's get to the next slide here. Now we're going to look at the different loads, but then we're going to try to calculate the reaction loads for this first free body diagram. And this we already know how we do it. First thing we're going to do is look at what kind of loading we have and moments we have, FZ and MY, or PZ and MY. Y would be the moment about the axis going along or into the plane of this page now. Okay, so that's what MY would be, because our axis system now is X going right, positive, Y going along PY, and Z going along PZ. All right, so for this free body diagram, what we have is a force balance. We start with that typically, and we have sigma FZ is equal to 0, sum of forces along Z equal to 0. So what that means is the fastener tension RFT would have to equal the sum of this PZ and RHT over here. That's what we have here, right? So now we get into the moment balance. And for the moment balance, what we have is sigma my equal to 0, right? The moments produced about the y-axis, which is basically, let's assume an axis that comes out of the plane of this slide, maybe somewhere here, maybe here, whatever, let's say the fastener. So the moments about that would be, the sum of the moments would be 0. So that's what we have here when we take the moments about this fastener axis, as you may have seen in that first YouTube video on heel toe loading. What we get is the PZ times the moment arm x2 here about this fastener axis would have to equal the reaction due to the heel toe effect underneath the bracket over here times the 2/3 the distance of this edge of this bracket to the fastener axis. So that's what we have over here. Okay. So when we substitute, from this equation, what we get is the heel toe reaction, and we simply rearrange this equation to put RHT on the left hand side, and therefore we get RHT, which is the R heel toe, as this equation over here, PZ times x2 times 3 divided by 2 times x1. Okay. So the next thing is that this yields the fastener tension, which basically says the fastener tension RFT equals to PZ plus RHT, so which is this guy here. So we simply add PZ to the heel toe reaction to get our fastener tension. However, this is the total fastener tension load. Because this, we are assuming it's shared equally by the two fasteners over here, so we simply divide this entire reaction by 2. Now notice here that I have a negative sign, right? And the reason for that is because the RFT is going down, and in our sign convention, PZ is positive up, and any load going down is negative along Z. Okay, so that's why we have that negative RFT. All right, so the next one would be the free body diagram due to PY, and we have already seen this. Now our job is to calculate or find equations for all of these different unknowns, okay, based on what we already know. So the first thing would be what are the different forces and moments we are going to be looking at: Fx, Fy, Fz, Mx, and Mz. So let's break it down one by one over here. Let's start with our force balance. So in the force balance, what we do is we first look at Fx going along this red axis over here. Okay, any loads and reactions along that axis. So sigma Fx equal to 0. So therefore what we have is the absolute value of this Rx1 going that way, which is equal to the absolute value of this Rx2. Okay, now these are reactions only. We don't really have any applied loading. We just have a reaction due to moments. Okay, and therefore these two are equal to, let's assume, Rx. Okay, and we'll get to this later on, but this is our sigma Fx equal to 0. This is an equation of unknowns that we don't know. And the next one would be sigma Fy equal to 0, and in this case the y is going along this Py axis, and therefore we have the reactions Ry on these two fasteners equal to Py over 2. So they're equally split between these two fasteners, and the reaction would be half of this applied Py loading. Okay, due to this Py we have these Ry reactions. The next equation is sigma Fz equal to 0, and in this case we have the absolute values of these two fastener reactions due to the applied moment from this Py about this x-axis. That's what that is. So this Rz1 and Rz2, these two values are like a force couple, and they will be equal and opposite. Assume like this is a cantilever beam, or just a beam, or a rod, where you are applying this moment at the end of that rod. Okay, so if you can idealize this portion on the bottom and remove this and just put this moment at the edge of this rod, so that's like applying a moment of Py times Z, and then you have a reaction couple, which is a moment that is opposite direction reacting this torque over here. So that's kind of the concept here. That's why we have these two reactions, and both of these we don't know what the values are yet, but we will assume both of these are equal to the value Rz. So these are our force balance equations. Next, what we'll do is we'll get into the moment balance. The first equation of course is Mx. Mx equal to 0. And what is Mx? Mx would be the moment caused by Py times the vertical distance z over here. So that's the moment about this x-axis over here. Okay, so this z would be from the top to the bottom of this angle bracket. Now remember that this bracket is a very thin bracket, so we just go to the bottom to get the easy dimension of this moment arm. Okay, so this bracket may be, you know, like a 1/8 inch bracket, let's say. So that's Py times z. That gives us the mz, or the moment about mx, that is the moment about this x-axis, and this moment has to be balanced or taken out by this force couple, which is assumed to be rz times the distance between the force couple, which is y, or the distance between the two fasteners over here, as you can see here. So that's the equation that we have for the sigma mx equal to 0. So this applied moment is balanced by this force couple. So that's what this equation is giving us. The next one would be rz equal to Py times z divided by y. So from this, we calculate what the rz reaction is, because we know Py, we know z, and therefore we get the value of rz. All right, so the next equation is sigma mz equal to 0, and this is the moment that's caused due to Py, this entire angle acting as a shear clip. Basically, that's what this would be like. So let's say you have fasteners over here trying to pull this thing along y, so then this whole bracket would be acting like a shear clip. And that's another thing that I cover in one of the blog posts in the stress engineering interview questions. You can go take a look at that. I discuss shear clips in there. And so due to this moment, what we get is that it's like a force that is applied right along this corner, and that is simply reacted along these two fasteners along the x-axis. And that equation would give us this Py times the distance from this edge all the way to the fastener axis, which is x2. So that would be your applied moment about the z-axis, right? That would be this vertical z-axis. That's why we have an mz here. And that would have to be balanced by these two reactions, which are basically a force couple, just like these guys were. And this is the anti-rotation type force couple. And therefore the moment for that force couple would be the force that is the same for both of these times the distance between the two fasteners, and that would again be y. Okay, so there you have that equation, and from that we can calculate what our x is, Py times x2 divided by y, right? So this Py times x2 divided by the distance between the force couple that reacts that moment. So what I've done here is I cleaned it up a little bit to include these absolute symbols here, just to make it a little more clear that we're looking at the absolute values here without the signs. But in the next slide, what we're going to do is we will get into the signs as well. This one here is the fastener reactions free body. It's not a free body diagram because we don't show you the heel toe reaction symbols here. With that, if you include that, then it would be a complete free body diagram, but I'm only showing you this figure to show you the reactions. Okay, so we're going to get into that. Now that we know what are the different equations, we can compile all the different reactions. So from the previous slides, we have Rx1. This is going to be a negative Py times x2 divided by y going along this way over here on the left, and Rx2 is positive going that way, so we have a positive sign, but the magnitude is the same. Then we have Ry1 is a negative Py divided by 2, because it's going along negative y. Same thing with our y2, same sign as well as the magnitude. And then finally we have our z1, which is the combination of the reactions from the free body diagram of py, which is this portion, and the free body diagram of pz, which is this portion, the heel toe part here and the force couple over here. So these two are negative. That means our Z1 over at this fastener is going to be the highest reaction. It makes sense because we're pulling this up, so that's causing a heel toe and all that. But then we're also pulling it this way, so this one would see the maximum tension load because of this type of loading over here. Okay, so that's this part. Then our Z2 even though this one shows up like that, it may not be up like that at the end. So this is just a preliminary symbol, preliminary vector direction, which may change depending on what we find out when we do some numbers. So here what we have is a positive force couple value from the PY free body diagram and the negative Fazener reaction from the original PZ free body diagram. So these two combine together to get you the RZ2 value at that Fazener. So these are our equations, and let's plug in some numbers into these equations to get into some sort of a real world scenario. So let's look at this guy here. What we have here is the same diagram again, but now I have added all these dimensions. So let's assume that this is a 1/8 inch thick thin little bracket, more like a shear clip, but it's a simple bracket, L bracket. And so this whole bottom edge would be 5 inches, and this is also 5 inches, and even this guy is 5 inches. Okay, so I think there's a mistake here, but I'll get to that later. Assume that x1, which is the distance from the fastener to this left edge here, that part is 1 inch. Fasteners are 1 inch in from that edge, and the x2 would be the remaining of the 5 inches, so that would be 4 inches from the fasteners to the corner. This y actually should be, I believe, 3 inches, because these fasteners are 1 inches in from these edges as well, so the distance between them should be 3. So this is a typo, I'm sorry about that. It should be 3 inches. The z here should be 5 inches. And we don't have an applied load along x. There we do have an applied load along y and z, each 25 pounds in this case. All right, so let's get into the calcs. Rx1, we substitute the numbers and we get negative 33.33 pounds. Going to the left here, Rx2 is the same number but positive going to the right. Then we have Ry1, which is half of the applied PY, but Ry1 and Ry2 both should be negative. I don't have the signs here, I don't know why, but I should have put them here as negatives. And then the next one, we're looking at RZ1. In this case, we substitute all the numbers and we get a negative, roughly, rounded up to the nearest whole number. We get negative 130 pounds at RZ1, which is the highest reaction. Then at RZ2, what happens is a reduction in the negative load of this guy due to this positive load. So we only get a negative 46 pounds. Now it's interesting to see that even though this thing was up in the previous slide, now this thing is down, because at the end, both of these reactions would be trying to hold this clip down, right? Because of the way we're loading it, this fastener doesn't see as much tension load as this fastener does. Okay, so that's what we need to take away from this. What I can do is, maybe in a future blog post or a future video, maybe we can do a little FEM comparison and see how well we did with our hand calcs, and just to see if the FEM kind of gives us a confirmation that our hand calcs are making sense, and so does the FEM. Is the FEM making sense? We can do a little cross check and see how we're doing. Okay, so thank you so much for watching this video, and I look forward to sharing more videos with you. And as I always say, please go to the blog over here and subscribe to the free blog. There are many options for you to join as a subscriber. As a free subscriber, you get many different benefits because of that. You get updates every time there's a new blog post. You get an instant email whenever a new blog post is published, and you also get a free ebook. My ebook that has been downloaded more than 4,000 or 5,000 times already, and you also get 14 CFR Part 25 regulations PDF with all the important regulations. I break it down. It's another bonus that I give you for free. You get that. You also get 2 free videos for the FEA course as well as the aircraft structures modeling course when you join as a subscriber, as a free subscriber. All of that is free. And you also, if you really want to get serious about learning, then you take it a level up and they take it a step further and become a paid member, and that's where you get the real bang for your buck and real knowledge that I worked so hard to put together for you, and that is only available to premium members. So I would love to see you become a paid member, and you can learn more about that if you go to this link over here. All right, so thanks guys for watching, and I will see you in the next video when we do an FEM comparison of this particular combined loading. And until then, Surya signing off, and I'll see you later.